Hello everyone, my name is Jishnu Rajesh Kumar. In this video, I am going to talk about a property of discrete Fourier transform, that is circular time shift property. Before actually talking about circular time shift property, I would like to talk about circular shift operation. Circular shift operation is an operation that we do in combinatorial mathematics, in which we take a set of values and we shift the values in either direction, left or right, by n places and move the last n numbers to the beginning. If we are shifting the elements by L places to the right, then we will move each element by L places to the right, and then the remaining L elements at the end will be moved to the beginning. The similar applies for left shift. It can be represented using the expression x of n minus L to the base n. Here x of n is the signal and n is the time domain index. L is the number of places by which we are planning to shift the signal x of n, and capital N is the number of points. It can be also expressed using the function in this form. When n is less than L, x of n minus L to base n can be written as x of n minus L plus n, and for n greater than or equal to L, it is just x of n minus L. This concept can be further understood by considering an example. Consider a discrete signal x of n as given below. X of n is equal to 3, 5, minus 7, minus 1 and 4, a set of 5 values. Let y of n be a signal which is obtained by shifting x of n by one place to the right. Here it is given as n minus 1 and hence it is being shifted to right. If it was n plus n, we will shift it to left. So we will shift these elements to the right by one place, and the last element, the last L element, which is last one element, which is x of n minus 1 or x of 5 minus 1, which is x of 4. Here x of 4 is 4. The last element 4 will be shifted to x of 0. We can implement this using the equations that we saw before. When n is equal to 0, which is less than L, x of n minus L to the base n is x of n minus L plus capital N. Here n is 0, so x of n minus L to the base n is x of 0 minus 1 plus 5, which is x of 4, which is 4. Thus, as we have predicted, we can see that x of 4 has been shifted to the place of x of 0, or here it is y of 0. So y of 0 is equal to x of 4. Now for n is equal to 1, here n is equal to L. So for n equal to or greater than L, we can just use the formula x of n minus L, which is x of 1 minus 1, which is x of 0 or 3. Thus y of 1 is equal to x of 0 or 3, and thus the signal has shifted to the right by one place. The same applies for 2, which is greater than L, and so on. Thus the signal x of n, in the signal x of n, 3 has shifted to the place of 5, 5 has shifted to that of minus 7, minus 7 to that of minus 1, minus 1 to that of 4, and 4 to the place of 3. And therefore we obtain y as y of n is equal to 4, 3, 5, minus 7 and minus 1. We can also see this using the graphs. Here this is the graph of the unshifted signal x of n. Here you can see this is 3, this is 5, minus 7, minus 1 and 4, the initial signal. And here y of n is obtained by shifting x of n by one place to the right. And just as you can see, the signals have been shifted by one place to the right. Now 3 is here at x, y of 2, and then 5 is at y of 3, and so on. And the last element, which was 4, is now in the beginning. Now let's move on to the actual circular time shift property of discrete Fourier transform. Consider a discrete time aperiodic signal x of n whose discrete Fourier transform is given as capital X of n 2 pi k by capital N or capital X of k. Then the circular time shift property of discrete Fourier transform states that the discrete Fourier transform of x of n minus n naught to base n is equal to capital X of 2 pi k by capital N times e power minus j 2 pi k n naught by capital N. Here the signal x of n minus n naught to base n is obtained by shifting the signal x of n by n naught places, and the DFT of this signal can be obtained by multiplying the discrete Fourier transform of x of n by a factor e power minus j 2 pi k n naught by n. Now let's see the proof of this equation. From the definition of discrete Fourier transform, We know that the discrete Fourier transform of a signal x of n is equal to sigma n is equal to 0 to n minus 1 x of n times e power minus j 2 pi k n by capital N. We replace x of n with x of n minus L to base n and we get this equation. Let this equation be equation number 1. Now we need to split the x of n minus L to base n term, or we need to expand this term. To do that, we are going to split the summation into two ranges. Thus we split n is equal to 0 to n minus 1 into n is equal to 0 to L minus 1 plus n is equal to L to n minus 1. In the range n equal to 0 to L minus 1, n is less than L. Therefore, we can write x of n minus L to base n as x of n minus L plus n. Similarly, for the range n is equal to L to n minus 1, n is greater than L. Therefore, we can write x of n minus L to base n simply as x of n minus L. When we substitute this in equation number 1, we get it as follows. Thus, we have split the equation number 1 into two terms and then expanded x of n minus L to base n. Let this be equation number 2. In equation number 2, next we are going to substitute the value of n minus L plus n and n minus L with the dummy variable m. Consider n minus L plus n. We substitute n minus L plus n with m. That is, m is equal to n minus L plus n, or small n is equal to L plus m minus capital N. Now when n is equal to 0, m is equal to n minus L, and when n is equal to L minus 1, m is equal to n minus 1. These are the limits for the summation. When we substitute this in this expression, we will get the term as follows. Here, this exponential term can be split into two, one with L plus m and one with n, like this. Here, e power j 2 pi k by capital N into capital N is equal to 1, because it is equal to e power j 2 pi k, and e power j 2 pi into an integer is always equal to 1. So thus this term becomes 1, and we end up with this expression. Similarly, we substitute n minus L with m. When m is equal to n minus L, n is equal to L plus m. This will substitute in the exponential term. Similarly, when n is equal to L, m will be 0, and when n is equal to n minus 1, m is equal to n minus L minus 1. When substituting these values, we will get this term. Now we will end up with these two terms. That is, we have converted the terms in terms of L and n into m and L. Now we can substitute this in equation number 2, and equation number 2 becomes like this. Here the terms inside both the summations are same, only the range differs. Therefore, we can combine these two summations to get a single summation from 0 to n minus 1, and we get the expression as above. Here again we can split this exponential term into two, one containing m and another containing L. Here L is a constant, therefore e power minus j 2 pi k L by capital N is a constant. Now this remaining expression reminds us for the equation of discrete Fourier transform for a signal x of m, which can be replaced by a capital X of k. Now we can replace this whole expression by capital X of k, and this equation becomes this. This is same as the equation that we saw in the beginning, and thus we have proved this relation. Now let's consider an example. Consider the same signal that we took for circular shift operation. X of n is equal to 3, 5, minus 7, minus 1 and 4. And the shifted signal y of n is obtained by shifting x of n by one place, which is 4, 3, 5, minus 7 and minus 1. When we take the Fourier transform of x of n and y of n, we get capital X of k and capital Y of k. These are the values that we obtain. But how do we validate whether this value will be the same when we do it using circular time shift operation? To do that, we will find y of k not by taking the Fourier transform of y of n, but instead by multiplying the terms of x of k by the exponential factor. Here, when y of 0, we take y of 0, it is equal to x of 0 into e power minus j 2 pi 0 by capital N, and this is 1 because it is e power 0. This is 1, which is equal to x of 0 or 4. Therefore, as we can see, x of k 0 and y of 0 are same in both cases. Now, when we take k is equal to 1, y of 1 is equal to capital X of 1 times e power minus j 2 pi by 5, which is equal to x of 1 times this value, which is e power minus j 2 pi by 5, and when we multiply it with x of 1, we will get this value, which is exactly same as the value that we obtained when we took the Fourier transform of y of n. Similarly, for all the values, we can see that the answer we got is exactly similar as the value we got when we took the Fourier transform of the shifted signal directly. This example validates the existence of this property. Now the same thing can be observed using graphs. These graphs we have seen in case of graphs. We've seen these graphs x of n and y of n in case of circular shift operation. Here x of n is the initial signal with 5 values, and y of n is obtained by shifting x of n to the right by one place. Now when we take the Fourier transform of x of n, which is x of k, and y of n, which is y of k, we get these plots, and the values are exactly same as the values we obtained by calculating, and these plots are plotted using only the real values. That's it for this video. The references that I used for this presentation is from Digital Signal Processing by John G. Proyakis and Dimitris G. Manolakis.